Okay, hi, we're going to be studying for the boards, NCERT textbook, class 11. And I decided to start with this chapter called Motion in a Straight Line. And what I'm going to do is teach you step by step, and we'll just go forward according to that. Step by step, whatever is written in the textbook, we'll go through each and everything. All right, so let's start. And I just have the textbook open in front of me right here, and I'm just going to go. I'm going to read everything and I'm going to explain everything little by little. So it makes a lot of sense to everyone. Mhm. So I'm just going to start and uh, kind of copy like the first main paragraph. I mean, not just one paragraph, the introduction, the entire introduction. And I'm just going to copy it on my window here. And it's okay, you can't read everything, that's fine. But I'm going to read everything and I'm going to explain everything, whatever that means. So here it says motion is common to everything in the universe. We walk, run, and ride a bicycle. Even when we are sleeping, air moves into and out of our lungs, and blood flows in arteries and veins. We see leaves falling from trees and water flowing down a dam. Automobiles and planes carry people from one place to another. The earth rotates once every 24 hours and revolves around the sun once in a year. The sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. What this paragraph is saying that everything moves, whether it's like within ourselves, like human bodies, small cells, atoms, and even like larger objects like the earth and the Milky Way. That's all this paragraph is saying, not very important paragraph. Next, we have motion is change in position of an object with time. How does the position change with time? In this chapter, we shall learn to focus how to describe motion. For this, we develop the concepts of velocity and acceleration. We shall confine ourselves to the study of motion of objects along a straight line, also known as rectilinear motion. So, it's giving some idea of like what motion is, and the basic definition is that motion we read until here. Okay. So the basic definition is that it's change in position, and whenever the position of an object changes relative to the observer, there is like we call it motion. Okay, and then it talked about motion in a straight line. If an object, let's say an object, let's have an object here, and let's say this object is moving in a straight line that is called rectilinear motion. Why is it called a rectilinear? That is not really important. Um, one thing I've learned while learning and teaching is when it comes to any new concept, we might wonder why this is happening or how this is happening. What I've learned is it helps that if we start something new, we just accept a few things that, okay, this is the way it is, because it will make more sense as you keep reading ahead. So rectilinear motion means that the motion is happening in a straight line. I mean, usually when motion happens, it happens in a lot of different ways. There are curves involved. It happens in a 3D space. But here we're just talking about a single line motion, and it's just called rectilinear motion. The chapter is called Motion in a Straight Line. So all we are saying is that the motion is along a straight line. Okay. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. So now this is a little bit ahead. We'll discuss this ahead. Just accept this for now. Even if you don't get it, it's fine. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. What is relative velocity? We will find out. Patience. In our discussions, we shall treat the objects in motion as point objects. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. So what is this trying to say? Whenever we are talking about real life things, whenever we talk about real life objects, maybe you have like your pencil box. You have a pencil box. It looks like this, maybe. Or maybe you can just think about like a duster in a school, which like your teachers use to erase your board, or whether you have a whiteboard or a blackboard. And it looks like this. Now, when we're talking about motion, this thing can also rotate like this. This thing can move in like a weird curved motion. But then because this object is so long, it's a long object, what do we decide? Like, there are many points in this object and the points can move relative to each other. So that can get confusing. So what we do in physics is We try to make things as simple as possible. And for that, we assume a lot of things. And when it comes to assumptions, one of the biggest assumptions we have in physics for learning simple physics, like the ones we learn in 11th and 12th grade, is that we can just imagine the object to be a point. The entire object can be just shown as a point. This is the entire object. That's it. And we imagine that this maybe like we take one point in the object which makes the most sense to us, and that is the entire object. And we just assume that this is a point moving, no matter what kind of motion it has, the point is moving. Now, when it comes to rotational motion, we usually do not consider the objects as a point, but that is coming later on. I'm just giving you an introduction. It's okay if you don't understand half the things I'm saying, or even like 90% of the things I'm saying. It will come to you slowly. All right, moving on. We had read until mm, relative motion till here. Okay, fine. Moving on. In our discussions, we shall treat the objects in motion as point objects, as we discussed already. The approximation valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. We already covered this. It's okay if it doesn't make a lot of sense. It's fine. It'll come to you slowly and steadily. Okay. In kinematics, now what is kinematics? Before I move forward, kinematics. So this word kind of has to do with this part of the word, which means motion in Greek. In Greek. Greek is a different language. That's okay. We don't have to worry too much about it. Basically, kinematics is the study of motion. And this whole chapter is about study of motion in a straight line. So this is part of kinematics. So in kinematics, we are studying motion. One of them is motion in a straight line. The other one can be motion, maybe motion in a curve, like or maybe in two dimensions. Now, what are dimensions? That's okay. If you don't understand it right now, this will be covered later. I'm not sure if you can see this. Let me have a look if you can. If I keep it here, is it visible to you? Yes, it is visible. Good. Okay. Coming back, coming back. Let's just finish this. In kinematics, we study ways to describe motion without going into the causes of motion. So we don't have to worry why the motion is happening. We are just worried about how it is happening. All right. Now, what causes motion described in this chapter and the next chapter form the subject matter of chapter 4? Again, they are just like there are a lot of things they are talking about. It doesn't make a lot of sense. That's okay. It will be covered later on. That's fine. So this is just the introduction, and that's okay. I mean, we are moving slowly. I mean, it might seem like you haven't learned anything, but this is how it works. We slowly move forward. Okay. All right. Moving on to the next part. Moving on to the next part. Instantaneous velocity and speed. So now sometimes like suddenly jumping into new words. Let me just copy this. Let me just put it back here. Suddenly jumping into new words can be confusing. This is part of the NCERT textbook. What does instantaneous mean? As soon as you look at this word, oh my God, I don't know this word. How does that even make sense? I've never heard of this word. I'm sure a lot of you have, but let's say you haven't. It's scary, right? And this is when we think that, okay, we'll study this later. It's okay, slowly. Instantaneous velocity and speed. So let's just read what it says. The average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity or simply velocity v at an instant t. Does this make any sense? No. I already know what instantaneous velocity is, but after reading this paragraph, it doesn't make much sense to me. That's okay. That's why I'm here. Okay. So let's read it again. The average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. Okay, now let's unpack this. Let's say, let's just take one object. We usually take point object, but like let me just draw a circle because a point is very small. So let's say this circle is moving in a straight line. Okay, let's say it covers a distance. So let's say it moved from point A to point B in a matter of say 10 seconds. Okay, and it travels a distance of 200 meters, right? 200 meters, this is the entire distance from this point to this point. This distance is 200 meters and it's covered in 10 seconds. Now, what does average velocity mean? Average velocity is just taking the total distance upon time, right? Now, when it comes to finding average velocity, when we are covering the distance, it just means like it doesn't matter how we've covered this distance. It is possible, for example, it is possible that maybe in this 200 meters, the first 50 meters were covered by, say, walking. You walked that distance. Rest of the trip was covered by running, for example. Or maybe there was another part of this trip. Maybe like somehow some friend came, they took you in their car and they covered the rest of the motion. It's unlikely, I know, but let's say this happened. So you were walking very slowly here, you started walking, I mean, you started running here, which is much faster, car is even faster. So when we're talking about average velocity, it doesn't matter how you're walking or how you're moving. All we know is that you were at point A, you moved to point B, total distance is 200 meters, total time is 10 seconds, and that's it. That's it. Average velocity is 200 meters by 10 seconds. So this is 2 meter per second. I know I didn't take a very good value. 200 meters is a very short time for walking, running, and a car. And 10 seconds, 200 meters in 10 seconds is a very short time. We can change this. Maybe we can say this was, say, 2000 meters, for example. And instead of this, we can say, let's say it was 100 seconds. Same answer. Okay. The idea is average velocity is 200 meter per second. It's 200, sorry, 2 meter per second. That's okay. That's average velocity. It is not concerning with how we are moving. And that's what this paragraph is trying to tell us. It tells us how fast an object has been moving over a given time interval. So among these 100 seconds, it tells us the velocity for the entire duration. But it does not tell us how fast it moves in different instants of time. So let's say the walking part happened for, say, 50 seconds, and this happened for, say, 40 seconds, and this happened for 10 seconds. So in these different intervals, the average velocity is not giving us information about these parts. Is it giving information? No, it's not. And that's what this paragraph is trying to say. For this, we define instantaneous velocity, or simply velocity at an instant t. Now, average velocity is not giving us enough information. So what we can do is we can start talking about instantaneous velocity. What is instantaneous velocity? What does this mean? A new term for most of you. Doesn't make much sense. It's okay. So now what we do is let's make this smaller. Like let's just say we check the movement of you in smaller intervals of time. Let's say we check every 10 seconds, or let's say we check every one. Let's keep it 10 seconds. So after 10 seconds, you were moving at a velocity of, let's say, I don't get into the nitty-gritties of this. It's okay. We're just thinking about, let's say, for like some duration of time, you were walking at, say, I don't know, 2 meter per second, and or maybe even slower. Maybe you were walking at very slowly, let's say zero point 0.1 meter per second. And then this entire, again, after the next 10 seconds, again, you're walking 0.1 meter per second. Again, 10 seconds, you're moving at 0.1 meter per second. It doesn't make a lot of sense. Like, because every 10 seconds, you have this particular velocity that you're moving at. But when it comes to running, maybe you're moving faster. Maybe you're going at 2 meter per second, which is a very small duration to run. But these are just examples. Don't get into like the technical aspects of it. In a car, maybe you're moving at, say, 5 meter per second. So what we are doing at every instant. Now people might wonder what an instant means. For every instant, it's a small duration. It can be as small as 10 seconds or 1 second or 0.1 second. Okay, and in reality, instant is supposed to be the smallest possible time you can take. And it can be very difficult to measure what an instant is, right? If it's so small, which is why we got something like limits. So let me just come back to the part we were learning. Yes. Okay. So let's just understand what these symbols mean. Delta x by delta t. What does delta x mean and what does delta t mean? What does this sign delta mean? So delta is, I think it's a Greek letter. So in English, we have like a lot of letters. We have A, B, C, D, and so on. In Greek, we have alpha, beta, gamma, delta, epsilon, and so on. Now, in Greek also, we have capital letters and small letters. So similarly, this is the smaller version of delta. In capital, we write it like this, like a triangle. These are just symbols. And in English, like you tend to like run out of symbols all the time. So we use Greek letters. So yes, even alpha and beta are used for a lot of things in physics. For example, there's an alpha particle, a beta particle, there's gamma rays, and a lot of letters are used for a lot of purposes. And these become like standard symbols. These standard symbols are used for different occasions. So when we talk about delta, we usually mean change in motion. Sometimes the same letter can be used in multiple areas. Sometimes like you can use it for multiple purposes. Delta can also mean something else at times, but usually it means change in motion. I'll just get some water. So I started with this chapter as an introduction. Of course, we could have done units, measurements, and stuff like that, the first chapter. But I started with the second chapter because I think like it gives us a higher feel of what we're getting into. We will cover the first chapter later. Okay. What I'm trying to say is a small instant. So before coming to an instant, we can talk about change in motion. How does change in motion work? Change in motion is more about, let's take something simple. Let's take like a number line. We have been learned about number line. Let's say it starts from 0, 0, 1 meter, 2 meter. Yes, you can think of it as a ruler, except like there are meters in between them and so on. It's a number line. 1 meter, 2 meter, 3 meter, 4 meter, 5, 6, 7 meter. And let's say you start from 0. Okay. You move from point, let's call this point O, point O, 0 or 0. The position of 0 is point O. And let's say you move to 4. You travel 4 meters and you reach point A. And then you travel 2 meters and then you reach point B. So what is happening? You started with O, you went to A, and then you went to B. Okay. Now let's say somebody wants to know the change in position from point A to point B. So what is the total position in point B? At point B, it is 6 meters, and at point A, it is 4 meters. Now change in motion from let's say X. What does X mean? Now, uh, let's just write this for now. Delta X is equal to 6 meter minus 2 meter. The change in position has been what? 4 meters. Sorry, I messed that up. Change in position has been 2 meters, right? So, what we're trying to say is like we're assigning a position to every point, like the movement. So, let's say point A, we have 4 meters, the change in position, and point B, the change in position is 6 meters. And when we talk about X, what does X denote? X is just X is a variable, we all know that. And usually when we talk about X, we talk about where the position is, position of an object. So for the first position, let's say we call it X1. So X1 is 4 meter, X2 is 6 meter. Delta X is X2 minus X1, change in position, which is 6 meter minus 4 meter is equal to 2 meters. This is just brushing up some basics. Sometimes it can be very confusing if you just start reading the NCERT book and you don't understand anything. So, yes, let's just finish this off. The velocity, let's just read the rest of the paragraph. The velocity at an instant is defined as the limit of the average velocity at the time interval. Delta t becomes infinitely small. In other words, so and so. Doesn't make much sense now, does it? It's okay. Basically, when we're talking about changes and we make the changes smaller. So right now the change is very big. Change is 2 meter for delta x. What we do is we try to keep delta x really small. So we try to reduce it. Maybe we make it, let's say we make it 6 meter minus 5 meter because we want to know the change in, we want to know the velocity. We want to know the velocity at 6 meter at point B, for example. Where was point B? Here, at point B, for example. So let's say we bring point A closer. Let's say we bring point A closer. Let's say 5 meter. The distance has changed. We went from 2 meters to 1 meter. Then we bring point A even closer. Let's say this is even closer. This distance BA even closer. Why are we bringing it closer? Because we want to find the velocity. We want to find the velocity at that position. So right now what we're trying to do is we know the formula. We know the formula that velocity, average velocity is delta x by delta t. We already know that. That's fine. Now, if we make delta t really small and delta x really small, it becomes dx by dt. Now, what is d? What is, these are all new things. That's okay. It's fine. What does d mean? What does delta mean? So, when we make delta really small, what do we mean by delta? The change in position. And we do change in time really small. What is actually happening here? What we're doing is we're taking smaller measurements. So instead of measuring at every 2 meters, for example, or every 1 meter, for example, we start making smaller and smaller measurements. We start taking measurements after every, say, zero point 0.1 meter or every 0.01 meter. And when our measurement is small enough, we can get a good approximation of the velocity at almost that point. Now, obviously, you cannot make the measurement so small as in like it's like, let's say it's 0.00000001 meter. It's hard. It's hard to make measurements in physics. But let's say it was small enough. It was small enough, then we can make it dx by dt. And what does d mean in this case? It's just delta, except when the measurements are small, we denote it as d, a small d. So coming back at what the textbook says, we are limiting delta t to 0. Now, what does that mean? What does that mean, delta t to 0? Huh. Wait, let me see what symbol they've used. Have they used change in, yes, delta t, right? Delta t tends to 0, which means, what does tending to 0 mean? Is just making the measurement smaller. When we're talking about 1 meter, for example. But in time, it will say, let's say we're taking 1 second. So one thing we can do is we can take intervals of, say, 10 seconds. Every 10 seconds, we make a measurement. That is easier. Every 10 seconds, you can even do it manually. Like you can just start, like, you can just keep on seeing, okay, like, okay, at this point, this was the position. After 10 seconds, this was the position. It's easier. But let's say we start taking measurements at a smaller time. Instead of 10 seconds, let's say 1 second, and then we keep reducing it. Somehow, maybe we are using technology, but we're continuously reducing it. Let's make it, say, zero point 0.1 seconds, and then we make it 0.01 second. So what are we doing? This whole measurement system, we started with a bigger one, and we're slowly getting smaller. What is it coming closer to? Zero, right? It's not exactly zero. We can never get exactly zero measurement. Like, how do you take a measurement right after like zero measurement? It's the same measurement. But if we keep doing this, delta t is getting closer and closer to zero. And if that's true, delta x is also kind of coming closer to zero, right? I mean, of course, these are going to be different values. Let's say we measured after 0.01 seconds, right? Let's say the value becomes 0.02 meters, the change in distance. So what is happening? When we put delta x by delta t, we have zero point 0.02 by 0.01, and we have 2 meter per second, right? So these values are going to be different, but they're going to come closer and closer to 0. And when they're close enough, we can get a very good approximate value of instantaneous velocity. This is instantaneous, which means in that particular instant, which is a very small measurement, we get uh, this value, this particular value. And this is written as, if it is very good enough, we call it dx by dt. Instead of we replace the deltas by d, where we have an extremely small value, and we can actually, in theory, we can say that a dx by dt exists, which is just the instantaneous velocity of that time. Okay, so these things can be confusing, it's fine. And we are just talking about motion, but then as you can see, as soon as we move on to the first paragraph, you already don't know a lot of things. So in introduction, it makes sense that, you just think of it, we're spending so much time on learning something so minuscule, but this is important. If our base is strong, everything else moves better. Okay, thank you for attending this lecture. This is all for now. I'll keep uploading more. Thank you. Bye.